When you launch a projectile on level ground at an angle, it takes a certain amount of time to travel along its path for reaching the ground, and it also travels a certain horizontal distance. We call that the range. It travels a maximum height above the ground as well. And in this video, what we want to do is figure out what the range, this horizontal distance, really depends upon. And again, we're not going to get bogged down in a bunch of calculation with numbers. We could, of course, do that. Instead, we're going to analyze everything in variables and really extract the fundamental relationships that this horizontal distance depends upon for projectiles launched on level ground. Now, before we do that, you hopefully should have worked through a previous video. And if you haven't, I would recommend that you stop this one and take a look at the video on flight time for this problem, where we work out a solution for how long in time it takes for this object to fly through the air. And that'll guide you through the major process of what you're going to be seeing here. And before we get into that process, it's always a good idea to take a step back and just think about what affects a certain parameter that you're trying to understand. So in this case, what about the launching of this ball and the environment, such as like the planet Earth, ignoring air resistance, of course, what do you think affects the horizontal range? How far horizontally this object travels? Pause the video and list out as many things as you can think of that you think are really relevant. Don't just list out like a million things, but what's actually relevant for what could affect this horizontal range. Pause the video and list out some things. All right, so I've listed out three common things: launch speed, launch angle, and gravitational field strength. And a kind of a quick way to get to understand if something might affect another parameter in a physical system is doing what I could call extreme thinking, which is kind of a funny phrase, but the basic idea is just imagine taking whatever parameter you're thinking about testing if it affects another one. In this case, maybe launch speed, right? We're trying to say, does launch speed actually affect horizontal range? And just do some extreme numbers, like a really large speed, and then compare that to like a really, really small speed. And if you do that, you can kind of clearly see that, well, if you launched it with just a really small speed, it wouldn't go very far. And if you launched it really with a just tremendous speed, it would go a lot further horizontally, right? That makes total sense. Of course, keeping everything else constant, right? And then you can do that with the next parameter. So launch angle. Have the shallowest launch angle of all time versus a very steep launch angle, and that might help you understand it. And then same with gravitational field strength. Okay, so a nice little skill there. All right, so let's turn to first principles. What are the major concepts and equations that apply to this physical system? Pause the video and list out those ideas as best you can, and then we'll take a look. All right, so I've listed some things out here, similar concepts to what we've seen before. We see that gravity causes the vertical acceleration. There's no horizontal acceleration at all because there's no net horizontal force. Again, we're ignoring air resistance here. And when the ball's flying through the quote-unquote air, even though we're ignoring air resistance, there's nothing else that's pushing or pulling on the ball except for the downward pull of gravitation. And then independence of horizontal and vertical motion. Movement in the horizontal direction is not affected by anything vertically, and movement in the vertical direction is not affected by anything horizontally. There's an independence of horizontal and vertical motion. And then I've listed out the two main equations that we would use. One of them is for horizontal position and the other one is for vertical position. And we can use both of these to figure out our result. All right, so I've got everything kind of written out from our first principles, where I've got my horizontal equation over here and my vertical equation over here. And notice I haven't tried to simplify these equations yet. I just wrote them out exactly how they come from the equations of motion. That's our first principle, and we know that that applies here to this physical system. I've also broken down the velocity vector over here to put that on the page so I can see it, and I've made sure to get all my subscripting right with my using y for vertical and x for horizontal. So notice before I even have tried to do any thinking, I'm just getting that, I'm getting those equations on the page visually, getting all that information out of my head so I can see it. And that helps free up thinking power so we can do the harder thinking of working with the equations and trying to figure out how to use them correctly to get to the final result, and also what concepts are relevant and how those help us kind of get to our theoretical result. You'll see what I mean here in a second. So let's start in the horizontal direction and think back. There's a concept that we listed just a second ago in the horizontal direction, and I want you to pause the video and see if you can figure out how we could apply that concept in the horizontal direction to simplify this equation. All right? Hopefully you've seen this before, but just another reminder of how important it is to write out these concepts because they help us simplify as we work through. Pause the video and try that. You did it, and you noticed that there's no horizontal acceleration at all because there's nothing pushing or pulling on our object horizontally as it's moving through the air. And again, we're ignoring air resistance. Now, gravity, of course, is pulling, but it's pulling straight down, and that's going to cause vertical acceleration, and that's where we take care of that over there. We can also set our initial horizontal position right here to 0 arbitrarily. It's a common choice there, so x is equal to 0 right there at that point. And that turns this horizontal equation into something pretty easy. So the final horizontal position, all the way over on the right, or our range, if you will, is equal to the initial horizontal velocity multiplied by the flight time, the amount of time it takes for this object to go from where it was shot all the way to right before hitting the ground over there. Now, if you've already seen the video on flight time, you should know what to do next, hopefully. But if you haven't worked out the flight time of this object, do that now over here using this equation on the right-hand side. All right, so go ahead, pause the video if you haven't done it, and work out the flight time. All right, so let's just take a look real quick, just in case you haven't worked it out. Do it kind of quick. And for the flight time, what's interesting is that the final position and the initial position are identical because we get launched at the same level. That's what it means to launch on level ground. In this case, you'd probably choose y is equal to 0 for the ground level, but you could also be on top of like a mountain or something. I don't know, like what if this was on some like hill or some canyon or whatever, or on top of a canyon. I don't, I don't know. This could be like 30 meters up in the air, and both the initial and final vertical positions would be identical, so they would cancel out like that. All right, let me just erase that because it's annoying me. Okay, we keep going. So we'll plug in over here, and we get 0. I'll just leave the units off for simplicity. 1/2 minus g t squared plus vi yt, and we solve for the flight time, and we'll put FL there for flight, and we get 2 times VIY divided by g. Cool. All right, so we've got an equation here that gives us our horizontal range. That's essentially what this is now going to be, our final horizontal position, and then our flight time. All right. So go ahead, pause the video, and now use both of those in conjunction and see if you can get to our next results, which is solving for the horizontal range in these variables that we see down here. Pause the video and try it. All right, so let's take a look. There's so much cool stuff to talk about here. But mathematically what we've done is we just took our flight time expression, which remember only depends upon the initial vertical velocity and then the gravitational field strength, and we plugged that in here over into our horizontal equation. And I've changed the subscripting from final, that's a little vague, to now range. So that communicates this is the horizontal range of our projectile. And of course, this is on level ground as well. So we're keeping that in the back of our minds as well. Now, if we look at the results here, let's try to extract some relationships and just do some high-level thinking on what we're looking at. The result is really, really cool. Put a box around this. Like, what is it saying, you know? Maybe pause the video. Yeah, pause the video for a second and just try to like think through this. Like, what is this saying about what the horizontal range depends upon? And is there any kind of like special way you can look at this? I know that's kind of vague, but just sit for a second and maybe just stare at this equation for a little bit and see if you can just kind of think about what it's telling you. All right, go ahead, pause the video. All right, so what stands out to me when I first look at this equation is right here. And what I'm noticing is that both the initial horizontal velocity and the initial vertical velocity matter in determining what that horizontal range is. So it means that both the motion horizontally and the motion vertically is important to think about. Now, that's further visualized if you imagine the particle right when it's launched down here, and you superimpose those components, the horizontal component of velocity and the vertical component of velocity, onto the picture. And I've kind of shown a steeper launch angle here. And you can see that there's a lot more initial vertical velocity to start with than there is horizontal velocity. But that vertical velocity is going to be decreasing. It's going to go all the way to 0 by the time you get up here. And that horizontal velocity is just going to stay constant the whole time. It's always going to be traveling to the right at exactly the same speed throughout the entire motion. But what you're seeing is that it's important to know both of these quantities right at the start, and they matter for determining what the horizontal range will be. Okay, now there's something hidden in here that's like finding like a gem buried under the ground or something. It's pretty cool. And I want to see if you can find it. All right. And I put a box around this in red. So you're still looking at this, all right? But then I've drawn another little picture over here. So we've got kind of like two launches. We've got this launch that's pretty steep, and then this launch that is not as steep. Okay. And I want you to look at the components. Then I want you to look at this. And then go back to the components. Look at the components, each set, and then look at this. And then do that a few more times. And if you do that correctly, you might see something that is incredible. All right, go ahead, pause the video and see if you can find the hidden gem. Maybe you got it, but if you didn't, one more little hint or help for you would be I put some numbers. I've left off the meters per second for clarity. Put the number 3 here and the number 5 there. And then I've labeled these numbers down here. Keep going. See if you can find it. All right, so hopefully you're seeing it. You're seeing that this first launch at kind of a steep angle, it doesn't have much horizontal velocity. So there's this tendency to think that maybe it's not going to go that far horizontally. But it does have a lot of vertical velocity. Compared to the other launch, which is at a much shallower angle, it certainly has a lot of horizontal velocity. So you reason, well, it's going to go pretty far horizontally. But it just doesn't have that much vertical velocity. So like, what does that even mean? Well, we know it's if you don't have much vertical velocity, you're not going to be flying through the air for that much time, right? But you are traveling pretty fast horizontally. And so you can see, because up here in the numerator, it's the initial horizontal velocity multiplied by the initial vertical velocity. Mathematically, well, if it's 3 times 5, that's the same as 5 times 3. So we can kind of see for these special angles, if you will, there's going to be situations to where we're going to have one of the dimensions make up for the other one in a sense. And we're seeing that here with these numbers 3 and 5 kind of swapping in the initial velocity components. So you might be wondering, I mean, is there some rule for those angles? And we'll get to that soon. But I want you to see right now how important both of these factors are, the initial horizontal velocity and the initial vertical velocity. All right, now let's go a little bit further, and why don't you just extract the relationships here, and there's really just 2 of them I want you to focus on, okay? Just 2 relationships, and see if you can write those down correctly. All right. So here they are. We've got the inverse, like we've seen before with the gravitational field strength. It should make intuitive sense. And the reason I kind of constrained my question to just 2 relationships is because I like showing it like this, where the range is proportional to the product of the initial and vertical velocities, where product of course means the multiplication between 2 quantities. So you could see how we could use proportional reasoning here, where we'd have to be thinking about 2 things at once in order to predict the range. So if we change the initial horizontal velocity by some factor and the initial vertical velocity by another factor, we could predict how the horizontal range would change. Okay, now though, think to yourself, well, what really determines what these initial velocities are going to be? Like, how do we get a sense of that? Well, we just recall that these initial horizontal and vertical velocities become known only when we know our launch speed, which is the magnitude of our initial velocity vector, and our launch angle, which allows us to break that down into components, horizontal and vertical. So over here, we certainly have a lot of horizontal initial velocity, but we don't have much vertical, and then vice versa over here in this much steeper launch. So with that in mind, with now knowing that it's really that initial launch speed and launch angle, those two things kind of in conjunction together are helping us understand these parameters up here for our initial horizontal and vertical velocities respectively. How can we then rewrite our horizontal range equation in terms of launch speed and launch angle? So pause the video now and see if you can do that. You'll need a little bit of trigonometry here in order to do it. All right, so if we just plug in for the initial horizontal and vertical velocities using v cosine theta and v sine theta, so we're writing in terms of launch speed and launch angle, we can transform our equation to something that looks like this over here. So hopefully you got that. But then let's kind of clean that up a little bit. So what would you do? Well, you just need to do some multiplication. And just watch out. Sometimes students make a pretty simple mistake. This would be v squared because it's v times v. And then we have a cosine of theta multiplied by a sine of theta, all divided by g. All right, so there's a nice little formula for our horizontal range. Now, though, what's really cool is to think about, again, what this formula is saying and what it means. Now, it doesn't mean anything new than what we have just talked about, but it's another way to look at it because it's written slightly differently. Now we're talking about launch speed here, and then we also have something to do with angle in our response as well. All right, so I've rewritten it up here so we can see it a little clearer and defining the terms of launch speed and launch angle. And we want to make sure we understand how this has meaning to us and how it helps us see the world in a new way. I always use the analogy of like a little radio where we've got these dials and we can change launch speed, launch angle, and gravitational field strength in any which way. And that would give us information about the horizontal range and how that would change. So why don't you focus in just on how launch speed, v, affects horizontal range. Extract the relationship that you see looking at this formula here, right? And then come up with your own example of a base case and then changing that by some factor to see how the range changes. Maybe think about kind of a scenario in your everyday. Maybe if you're into sports and you play football or baseball or soccer or something where there's like a ball flying through the air, right? I think you can imagine something like that. And you totally ignore air resistance. How can this formula help inform what happens, all right, when we focus in on launch speed and horizontal range? Pause the video and come up with your own thinking on this, and then we'll take a look. All right, hopefully you've seen it. And there is a squared relationship between the launch speed v and the horizontal range. And so I have an example of if we were to double our launch speed. I've shown that here. So here's a base case where we launch at some speed v, and then we double that speed to 2 times as much. Well, the squared relationship would predict 4 times as much horizontal range. I've indicated that by just labeling my horizontal range as a distance d. Sometimes we do that instead of using x. And we would see 4 times as far. Now that's pretty cool. I mean, imagine if you had a baseball in your hand or a football or kicking a soccer ball or just some object that you wanted to throw, right? Yeah, well, if you could throw it at exactly the same angle on the same planet, ignoring air resistance, and you could double how fast you threw it, it would travel 4 times as far horizontally. It's really cool. It's kind of, I mean, you might think, well, if I threw it twice as fast, it would only go twice as far horizontally. Well, that's not what's happening. It's going 4 times as far. So you can see how important this relationship is. All right, now as a curious thinker of this physical phenomenon, you might look at this picture that we've drawn now and say, wait a minute, look at this. My horizontal range is quadrupling. What about my maximum height? How would that change? I wonder if I could figure that out. Well, you can, right? So maybe pause the video, come up with the specific equation now in terms of, and I'll give you a hint here, you're also going to have launch speed, you're going to have launch angle, and you'll have the gravitational field strength. All three of these things will show up in a specific equation that would allow you to predict the maximum height. And we'll write it right here, y max. We've seen this before in one dimension. Give it a shot here now and see if you can get it, and then I'll show you the result. Pause the video and try that. All right, well, hopefully you followed the process and you were able to create this specific result where we have the maximum height is also the squared relation with launch speed. Then we see this pesky little sine squared theta pop up, interesting, and then divided by 2g. So if we extract our relationship now, we notice very clearly that the maximum height is proportional to the square of the launch speed. So we would also see a quadrupling in our parameter here, the max height, just as in the range if we were to double our launch speed. Now, I hope you're seeing really how much information is encapsulated in these formulas and how it's just so much more than things that you plug numbers into. Right? It really tells the story of this physical system and gives you like really deep understanding. And if we come back to this other formula we started with for the horizontal range, where we get this product of the initial horizontal and vertical velocities, let's try to make sure that that kind of connects with what we just did, where we looked at the launch speed and launch angle, right? And if you think about our base case over here, where we're launching at some angle, at some launch speed, and then we doubled that launch speed, but we kept the angle the same, and the same gravitational field strength, of course, then we should also see that the range quadruples, right? So how do we get to this proportional reasoning where we get a quadrupling in the range? Now we're doubling our launch speed, but that launch speed variable is not in this equation now, right? Instead, we have initial horizontal velocity and initial vertical velocity. So pause the video and see if you can look at these two triangles and prove to yourself that we will still get 4 times the horizontal range, but your analysis should be geared more towards looking at these components and not towards looking at this total launch speed. All right, pause the video and see if you get it. Specific equation, extracting relationships, proportional reasoning. The process, we're doing it again here. Except these formulas just come from trigonometry. So we can see that both initial horizontal and initial vertical velocity are directly proportional to launch speed, assuming we have obviously a constant angle of launch. So therefore, if we double the launch speed, we're going to double both the horizontal and the vertical initial velocities. So what that means, of course, is we're going to end up getting over here 2 VIX and 2 VIY. It's a pretty cool mathematical result that comes out of just the right triangle trigonometry. Now, because of those factors, if we recall and we extract the relationship between range and that product that we were talking about, like this, now we're doing proportional reasoning where two things are changing at the same time. What's changing? Well, we're doubling this term, and then we're also doubling this term. So we have two factors of 2, and 2 times 2 is 4. And so we've quadrupled the range. We've proven it. Now, I'll write it up here kind of in this way as well. The initial goes to 2 times in the horizontal, and then the initial in the vertical also goes to 2 times. So that's how we're changing the parameters on the right-hand side over here, and then we're seeing the result by applying the specific mathematical operation that the formula says to do, and in this case, it's just multiplication between these two. Now, we haven't even really talked about the angle that we're launching at quite yet in the context of this new formula here. So there's more to this story. Let's talk about that. So we'll assume that the launch speed is held constant now, and of course the gravitational field strength we're assuming this whole time has been held constant. But we're going to vary the angle at which we launch it. So here you can see a real steep launch, and here you can see a real shallow launch. Is one of these going to give kind of like a larger horizontal range than the other one? Are they going to give the same amount of range? What's going to happen here? Well, again, let's play around with the mathematical equations and see what happens. Okay, so maybe pause the video and think about that and just write down which one you think is going to have a longer range, or maybe they'll have the same range in general. I mean, I haven't given any numbers here, but just intuitively, do you feel like one of these things is going to have a larger horizontal range traveled than the other? Pause the video and just write down your initial thought here. All right, so hopefully you thought about some things, and I hope you thought that the one that's launched at a very steep angle like this, it's going to spend a lot of time in the air. It has a very high initial vertical velocity, and we've seen how flight time really depends upon that. So this one's going to be in the air for quite a long time. But it's not really traveling horizontally that quickly. You can see by that component right there. Likewise, over here, we've got this projectile, and it has a much smaller vertical velocity to start with. So it's not going to be in the air for all that long. But while it is in the air, it's traveling really fast horizontally. So maybe these two effects can sometimes balance out, right? To where we're kind of making up for the fact that we're not moving so fast horizontally by being allowed to travel through the air for more time, and vice versa. So how could we kind of figure that out, right? Well, we could look at the parameters up here that have to do with angles, so cosine theta and sine theta, and just make up some angles and start comparing, right? So why don't we do that? Why don't we decide upon an angle for A of 30 degrees and an angle for B of, that's not right, sorry, an angle of A will be 60 degrees. It's a much steeper angle than B, and then B will be 30 degrees. That makes more sense. Okay. See what happens. Go ahead and plug in those numbers up here to our cosine of theta times sine of theta. Now watch out, you're not plugging in two separate angles. You have to do the calculation twice, right? So you're going to do cosine of theta times sine of theta for this one, and then cosine of theta times sine of theta for that one. Try that, see what happens mathematically, and see when you get the answer, which I'm sure you will, if you can just plug in for sine and cosine, what it means. What is it telling you, right? Pause the video and try it. All right, so I've done that over here on the right-hand side. Cosine of 60 times sine of 60, and this is where your automaticity of the sine and cosine function with different angles really pays off here. So you don't have to get bogged down in your calculator. Cosine of 60 you should know is 1/2. And sine of 60 is root 3 over 2. Multiply those together and you get root 3 over 4. Do it again over here for 30 degrees. Cosine of 30, well that's root 3 over 2. And sine of 30 is 1/2. Amazingly, we get the exact same factor. So therefore, if we launched it at 60 degrees, we'd produce a number, and I think I worked it out here. Let me just check my calculator. I'm going to have to do it again. Root 3 divided by 4 gives us about 0.4325. So if we launched it at 60 degrees, this part of the formula here would turn into the number 0.4325. And with the other angle, it would do the exact same thing. Meaning, when we calculated everything out, we get exactly the same horizontal range in both cases. That's pretty incredible. A 60-degree launch is identical to a 30-degree launch in terms of horizontal range. Not in terms of flight time. Clearly, this launch will have a much higher flight time. It'll be in the air for longer. But the ranges horizontally will be identical. Keep in mind, we're ignoring air resistance. That's a really big point. All right, now let's keep going. This is an amazing pattern, and when you kind of work through formulas and you discover something like this, then you should take a step back and say, wait a minute, that's pretty cool. I wonder if this pattern is happening again in another context, right? Because this is just one specific example. Think about it. Look at these numbers, right? Does anything strike you about the numbers I chose? Circle these. Just look at that for a second. Maybe you come up with a pair of angles, two angles. any angles you want between 0 and 90 degrees. But come up with two angles and see if you can make the numbers come out to when they're multiplied together with cosine and sine, you still get the same exact thing. Try that. I think you can figure it out. And then maybe try another one, and then another one, and then we'll see a really cool pattern. I think that you'll find so awesome. Pause the video, find some patterns. Go ahead. All right, well, here it is. I chose 80 degrees, a very steep launch, versus 10 degrees, a very shallow launch. Same operation, plugged all the math in, and I get 0.171 when I multiply. Now, if you don't believe me here, maybe just put it into your calculator. But cosine of 10 degrees ends up being the same thing as sine of 80 degrees. And so we get 0.985 multiplied also by 0.174, just doing all the numbers. And we get the exact same factor. That's pretty cool. Notice too how this factor up here, coming out of the multiplication of cosine and sine, that's a smaller factor than the one we had just previously done with the angles of 60 and 30 degrees. I think that factor was like 0.43 something. So now it's only 0.171 something. And if you just, do a little bit of math, just divide those two things. So 1.7, 0.171. Divide that by, I think it was 0.4325. And it's about 40%. So this factor here is about 40% of the other factor. So you'd see that the range was 40% of the range when we launched it at 60 and 30. Interesting, right? I mean, that should kind of make sense that it would be a smaller range. 80 degree launch is pretty steep. 10 degree launch is pretty shallow, and it kind of feels maybe like 60 and 30. We're getting towards maybe a larger value, right? And maybe you're starting to see, this is pointing towards this idea that there's going to be some special angle that maximizes this range. That gets us the furthest horizontally that we could possibly go. Wonder what it would be, right? Think about that. We'll come back to that in a second. Let's finish this pattern and notice what angles we had, right? I'll write this up here. It's getting a little messy here, but we had 60 degrees and 30 degrees, right? For A and B. What did we just test? Well, we just tested 80 and 10. Do I see a pattern there? I think I do. If I wrote this down, 70 and 20, you could figure it out again, and you know what you'd find? You'd still find that you'd get the identical ranges between the angles. So 70 degree launch would give you the same horizontal range as a 20 degree launch. What's the pattern? Well, if you add them up, you get 90 degrees. That's pretty cool. So if you're comparing two launches, all you got to do is take an angle, take your first angle, and then if the other angle added to that one is 90 degrees, then they're going to be identical launches. So if you launch it up at 85 degrees, almost straight up, but 85 degrees, well, the equivalent range launch angle for a real shallow angle would be 5 degrees. That's a cool insight that you kind of only get by playing around with the equation and looking at the math, which is awesome. Now I tend to like to leave the range equation in this form because, I'll look at maybe a really shallow angle of launch, and I can mentally easily see that the cosine of theta is going to be large and sine of theta is going to be small. And then likewise for a pretty steep launch, sine of theta will be a large number, but cosine of theta will be a pretty small number. Kind of makes sense that way to my mind, right? But there's another way that we can actually write this range formula that you might see. And I'll ask you to pause the video here and turn this formula into a formula where these two things become just one thing. So we're not going to have a theta here and a theta over here. We're going to have just a single theta in a formula. And alarm bells should be going off in your mind right now if you've taken like a trigonometry class, because there are all these trig identities, as they're called, that allow you to kind of turn one sine cosine thing into another thing. And depending on your knowledge of those, well, now's the time to deploy that knowledge and you'll see something cool. So go ahead, see if you can figure out the trig identity that consolidates that cosine and sine into one term instead of two. Have some fun. Pause the video and try it. Here we have it. It's the double angle formula. There's multiple double angle formulas, but this is the one we'll use. Sine of 2 times theta is the same thing as 2 times sine of theta times cosine of theta. So we've got our 2 right over there. There's our 2 there. Sine of theta there, and our cosine of theta there. So we can rewrite now our horizontal range formula. You often find this one when you look it up in like a book or something. And the formula we now get is v squared times sine of 2 times the angle of launch. Now we're still launching it at angle theta. Okay, just watch out. We're still launching it at some angle theta. It's just when we use it in the math equation, we have to multiply that angle by 2 if we want to use it in this formula. And then, of course, divided by g. We still have our squared relation with launch speed, still have our inverse relation with gravitational field strength. We're just writing the angle term slightly differently. Okay, so now, how can you use this to prove, I'll write it out here, prove what angle, there's a single angle, what angle maximizes the horizontal range? It's a great proof. And there's a couple ways to do it. If you've taken calculus, you can use your calculus knowledge, which is pretty cool. Or you can do it just in another way pretty easily as well, just by looking at the formula and testing out some numbers. All right, so go ahead, have some fun, and prove what angle maximizes the horizontal range. All right, well, here it is. And you should know from your math skills that the way the sine function works, the sine of whatever you put in here, the maximum that it can ever get is 1, right? And go from 1 down to -1. So the largest magnitude of whatever sine of some angle is going to be 1. So therefore, we need to solve for when this term here, sine of 2 theta, is equal to 1, and that'll maximize. And we're assuming launch angles between 0 and 90 degrees, of course. So when is sine of 2 theta equal to 1? That's what you should have solved for. And hopefully you can see, I'll write this over here, when theta is equal to 45 degrees. And we can prove that very easily. We'll plug in for sine. So take 2, multiply by that 45 degrees. And that's the sine of 90 degrees. And you should know that the sine of 90 degrees is equal to 1. So there we have it. We've proven now the angle that probably you thought intuitively, but it's cool to have this proof. Launch it at 45 degrees and it will go the furthest horizontally that it can possibly go. All right, now I've kind of cleaned this up here at the top. And, you know, if this term, sine of 2 theta, does equal 1 for that maximum range, the farthest it can go horizontally, is there anything else we can extract here? Well, yeah, I hope you can see it. We just multiply 1 times v squared over g, and now we've proven that the maximum range for a projectile launched at on level ground, which is 45 degrees, right, is just v squared over g. That's incredible. And that has come out of our analysis here by playing around with all the equations, stopping for a second, taking a look at them, and seeing what they really mean with abstract mathematical thinking. Now, surely you're saying there can't be more, right? Well, you're wrong. There is. There's more. Let's use more mathematical thinking, and I've put it here. What do you see on the right? Well, you see a graph. What am I graphing? Well, I'm trying to graph the horizontal range, how far the thing goes horizontally, versus what? Well, the launch angle. We vary the launch angle. It's really shallow, and we steepen it, we steepen it, we steepen it. We get to that 45, that's our max range. But then it gets steeper and steeper and steeper and steeper, right? And we get this graph. Well, what would the graph look like? Think about it. What would a plot look like? Pause the video, see if you can draw out the shape of the graph. And hint, all you got to do is look at the formula that's staring right at you at the top of the page. Think about it. Don't get too confused. Look at what we're graphing, right? Theta on the x-axis, or the horizontal axis, I should say, and then range on the vertical axis. Pause the video, draw the graph, and try to interpret what you're looking at if you do get it right. All right, go ahead. All right, so let's take a look. Now, importantly, please, you are not looking at the path of the object through space. This in no way is the path, even though it kind of looks like it. This is an abstract representation of how far it goes horizontally versus the launch angle if we were to vary that, and we're plotting that in a graph. Okay, so just watch out for that. Now, in math class, the function that we're plotting here would be something like, y is equal to some constant a times sine of 2x using generic math class variables. This has nothing to do with vertical and horizontal position. I'm just kind of trying to come back to that context in math that you're probably familiar with, right? Y is equal to sine of x. You know what that curve looks like, right? So here's a, which is just some constant out in front that corresponds to this constant here, which has physical meaning, the launch speed squared divided by the field strength, right? And then multiplied by the sine of 2 times some angle, which would just be x, and this is all in degrees. Now let's look at a couple important points on the graph. And the first one that seems obvious, hopefully, to you is this 45-degree angle. And if we were to just kind of go up here, all the way up to the top, and then draw a horizontal line over and read off what the horizontal range would be. A little mark right there, right? At 45 degrees, what's that horizontal range? Well, it's the largest it's ever going to be, but specifically, what is it, right? Well, look at the equation. When theta is 45 degrees, sine of 2 times that, 2 times 45 degrees, gives you sine of 90, and sine of 90 is 1. Right? So this thing here would just turn to 1 at the maximum launch angle like we've seen before, leaving v squared over g, the launch speed squared divided by the field strength, and that would be our range here. So this point on that vertical axis, which is the vertical axis of the graph, right, which is the horizontal range. Watch out with that terminology. A lot of times we use the phrase vertical to mean this up and down axis on a graph, even though it doesn't necessarily have anything to do with vertical up and down in the real world. We would label this as v squared over g right there. Okay, so that's cool. So that's our launch speed squared divided by the field strength at that point. And then we've got these other angles, and we think to ourselves, well, we saw just before that when we launch at two different angles, if they add up to 90 degrees, they're going to have the same horizontal range. That's awesome. So like 30 degrees and 60 degrees, that adds up to 90, so that would be the same range. 10 degrees and 80 degrees, 20 degrees and 70 degrees, those should all produce the same range. How does that show up on the graph? Pause the video and see if you can prove it to yourself how, for example, 30 and 60 are showing the same horizontal range on the graph. Go ahead, give it a shot. All right, so you can see I've done it here, and all we have to do is go straight up to where the curve intersects here and over to the left for both 30 and 60 degrees, and you can see it's at the same level here on this axis, so they have identical horizontal ranges. Now you can do this for other spots as well. Imagine drawing another horizontal line, maybe something, I don't know, like this. And at that spot, if we went down and read off the angles, kind of like right there, like what would that angle be? And then this angle here, sorry, it's getting a little messy there, but you'd have 5 degrees and you'd have 85 degrees for the angle. Right there, those add up to 90, right? Which comes from that principle that we learned before. So anytime you draw a horizontal line on this graph, you're picking out angles that will give identical ranges, and that's going to add up to 90 degrees. Pretty interesting finding from our theoretical expression here and our graph. Now the final thing we'll do here is think about what if we launched at different launch speeds. This graph, it just pertains to one particular launch speed, v, right? And we found the maximum range, v squared over g, and that was plotted up here. But is there a way to communicate a lot more information about many different launch speeds at the same time that we're allowing the angle to be different angles as well for our launch angle, right? We varied the angle from 0 all the way up to 90 degrees here, and for one launch speed, and then we plotted the results, right? So how can we get more information on this graph? Well, just consider what if we were to take our launch speed and cut it in half. Use proportional reasoning, pause the video, and what would happen to our range? By what factor would the range change if we cut the launch speed in half? Give it a shot. All right, well, you've extracted the relationship, and it's the squared relation. Range is proportional to the square of the launch speed, so when we cut this in half, we take the factor 1/2 and we square that and we get 1/4. All right, so the horizontal range would only be 1/4 of what it was before, and we could show that here on the graph. This would be somewhere around there, would maybe be 1/4 of the other one's horizontal range, and a plot would look something like this as we varied the angle. Cool, so we'll put in this one is a launch speed of v over 2. Now what if we decided, hey, let's have a horizontal range that's half as much as the original one? Well, on a graph, that would look maybe something kind of like this. And you can see here, right around there, it's about half of the original one right here. So my question to you is, what would this launch speed need to be? We're kind of going backwards now with our proportional reasoning. So we started with the launch speed of v. We got this plot with the maximum horizontal range. Then we cut that launch speed in half, and we only got 1/4 of for the horizontal range. What would we have to do to the launch speed to get half of this maximum range? Pause the video, see if you can get it. All right, now one thing you could do, you could just solve for launch speed, come up with an equation over here, a brand new equation, but I don't want to spend the time doing that. You can instead just kind of go backwards here. So we start with what's going to happen, and the range is going to be 1/2 of whatever it was to start with when we launched at launch speed v, and let's just kind of go up here. We remember that when we're doing this proportional reasoning, we do the factor, or we do the operation to the factor to see what the change is over here, by what factor the quantity changes by. So how do we get 1/2 here if we have to square something? Think about it. And that happens if you go 1 divided by the square root of 2. So 1 over root 2, when you square that, you get 1/2. So that's it. That's the factor. 1 over root 2. And what is 1 over root 2? Well, it's 1 divided by approximately 1.41. And if you type that into your calculator, 1 divided by 1.41, you're going to get about 70 something. And it's about 71% or so. So the launch speed, I'll just kind of write it out like that, now would have to be approximately 0.71% of the original speed. That's a pretty interesting finding in order to cut this range in half. And that, of course, would work for all of the angles that we shoot it at. All right, so that pretty much does it. We can take a big deep breath. We've done a lot of abstract thinking here. And you might be thinking, well, where would we go next with this type of analysis? Well, we've been in theoretical physics land right now. We've been doing everything from first principles with math, right? Working out expressions and just thinking at this abstract level. So where we would go next is the real world. We'd do some experiments. We'd set up an ability to change the angle, to change the launch speed, and take measurements and data, and then match those experimental results with our theoretical model here that we've built up. And if we find that those two match well, then we have great evidence to show that what we're doing here is likely correct. And it's a tough experiment to actually do in the real world because you've got air resistance and you got to get precise equipment. But there's certainly a lot of simulations out there where you can do this. And I'll just leave you with one of them that's really nice. If you go to the University of Colorado Boulder and you type in, just go into Google, PHET, Fett from the University Colorado Boulder. And they have a great simulation about projectile motion. And it gives you a lab that you can go through and play around with all this stuff and get your own data set and make everything make sense experimentally here. All right, with that, I hope you enjoyed the video, learned a lot here, and we'll see you next time.